Professor Liu Huaping. Professor Liu Huaping is a professor from Tsinghua University. He is with Department of Computer Science and Technology. His research interests include robotic perception and learning, and has published more than 200 papers in this topic. He served as area chair of RSS, associate editor of TASE, T-Septics, ACRA, IROS for many years. And he has received National Natural Science Fund from distinguished young scholars in 2020. Okay, Professor Liu, now stage is yours. Please, I'm looking forward to your talk.
Okay, thank you. First, I'm very apologize for my problem of my computer. And I can just connect this workshop via my phones. So I asked Professor Li Chang to help me to change the slides. And this slide is just a PDF file, so maybe some video will be missing. I'm very sorry for it. Okay, I will start my talk. I'm Huaping Liu from Tsinghua University. Very thanks for the organization of this workshop, and I'm very honored and happy to meet all of you online. The topic I would like to talk about today is Dexter's manipulation from multimodal perception to lifelong learning. Please, next page. Okay, this is the outline of my talk. First, let's talk about the motivation of this topic. Next one. Okay, the Dexter's manipulation is a very popular research topic in robotics and has been investigated for decades. It is never an easy task. As we can see here, the feature of the object can be complex. The manipulation environment for the robot is open, and the robot is usually faced with various tasks. All of these facts make the Dexter's manipulation very challenging. Accordingly, the robot is required to have the abilities from multimodal perception to lifelong learning. Next one. Okay, this is the article published in Science, which is written by Professor Billard and Professor Craig. The article talks about the trends and the challenges in robotic manipulation. It has clearly pointed out that the multimodal perception and learning are two critical aspects for robotic manipulation. We could make a comparison between human and robot, also quoted from this article. It says that the humans are proficient at alternating between different senses, from vision to touch and back, and can do so rapidly. By contrast, robots still lack the ability to decide what sensor to use, when to use them, and when to switch between sensors. Therefore, we believe that Dexter's manipulation should go from multimodal perception to lifelong learning. Next one. The next. Okay, now let's talk about the multimodal perception. Okay, the next one. Here is the overview of the multimodal perception of our architecture. It is mainly composed of two parts. The first part is intermodality. An active perception network is used to actively implement the modality selection. It decides which modalities we will use. The second part is intramodality. The action prediction network is used to actively select actions. For visual modality, we can select different viewpoints. For auditory modality, we can select different orientations. And for tactile modality, different exploration modes can be selected. In the following, I would like to share some of our work in multimodal perception. Next. This work is about the tactile fusion for object recognition. Tactile sensors are usually fixed on robotic fingertips, which can be used to distinguish material texture, roughness, spatial features, compliance, and friction. In this work, a Carlos bus coding method is developed to address the tactile data representation and classification problem. The intrinsic relationships between fingers are explicitly taken into account using the joint sparse coding, which encourages all of the coding vectors to share the same sparsity support pattern. Next one. Because of the diversity and uncertainty of objects and environments, common grippers with one single grasping mode face difficulties to fulfill all the tasks. Hence, a soft gripper with multi-grasping modes is proposed in this work. The soft gripper is able to realize 4 grasping modes, including wrap, pinch, hook, and suck. Next. Because more and more solid waste is generated, the management of solid waste disposal has become a global challenge. In this work, a vision-guided tactile material recognition method is proposed for waste sorting. The vision guidance module integrates an object detector and an affordance network together. It allows the robot to obtain a configuration to grasp the target and actively collect its tactile data. By classifying the object with the tactile data, the robot can sort the reusable objects into their respective categories according to the type of material. Next.
I cannot do that. I'm doing that, but I cannot. Moment. Maybe. Okay, now it's look like okay. Great.
Okay.
Sorry for that, please.
Okay. Currently, the most usual method is to detect the picking and the grasping points for some specific end effector into suction cup, gripper, or robotic hand. The manipulation performance is therefore strongly influenced by the visual module. Nevertheless, the conventional visual method often fails in complicated environments due to the mistake calculation results. In this work, we develop a novel framework to integrate interactive exploration with a composite robotic hand for robotic grasping in a complicated environment. The exploration strategy is obtained by the deep reinforcement learning procedure, and the experimental results show the proposed method significantly increases the manipulation efficiency. Next.
Okay.
Further, we investigate the cross-model material retrieval problem, which permits the user to submit a multimodal query including tactile and auditory modalities, and retrieve the image results of visual modalities. We establish a framework that deals with weakly paired multimodal fusion method for tactile and auditory modalities, and the weakly paired cross-modal transfer for visual modality. Such a framework may find extensive applications in many fields because it can be flexible to deal with a multimodal query and use the minimal category label supervision without the need of strong sample pairing information between modalities. Okay. It is still a great challenge for the visually impaired people to perceive their surroundings from a global perspective, which makes it very difficult for them to interact with unfamiliar environments. In this work, a new game model is developed to effectively transform the ground images into the tactile signal, which can be displayed by an off-the-shelf vibration device. The algorithm and the hardware are integrated into a portable device, which provides the visually impaired people with effective surrounding perception capability. The proposed work demonstrates the promising ability of artificial intelligence in healthcare applications, and the generated tactile signals are expected to be used in many human-centered systems. And we believe that this contribution is a very good, important step toward the development of a more comprehensive assisting technology for visually impaired people. Okay. In this work, we proposed a new task named manipulation question answering, where the robot performs manipulation actions to change the environment in order to answer a given question. To solve this problem, a framework consisting a QA module and a manipulation module is proposed. Besides, a novel data set that contains a variety of object models, scenarios, and the corresponding question answer pairs is established in the simulation environment. Okay. And the reference expression are commonly used when we refer to a specific target in our daily dialogue. In this work, we develop a novel task of audio-visual grounding reference expression for robotic manipulation. The robot leverages both the audio and the visual information to understand the reference expression in the given manipulation instruction, and the corresponding manipulations are implemented. It is demonstrated that the audio information is useful, especially when the referred objects are visually indistinguishable. Okay, next one. Then we come to the lifelong learning. Next. For lifelong learning for manipulation, the self-supervised learning and the robust manipulation are two important components. Let's first talk about lifelong cross-model learning. As mentioned earlier, tactile sensing has shown great advantages in capture material properties of object's surface. However, the conventional classification method may not work well during interacting with unfamiliar objects in unstructured environments. To this end, a visual tactile cross-model learning framework is proposed for robotic material perception. In particular, we address the visual tactile cross-model learning in the lifelong learning setting, which is beneficial to incrementally improve the ability of robotic cross-model material perception. Next. For the self-supervised learning aspect, we propose a new visual self-supervised method named invariance propagation. Different from other contrastive learning methods, we use a recursively discovering algorithm to incorporate different samples as positive samples. It has a fairly good performance and surpasses previous results. We also try to understand the behavior of the unsupervised contrastive loss. We show that the contrastive loss is the hardness aware loss function, and the hardness aware property is significant to the success of this loss. Besides, the temperature parameter plays a very key role in controlling the local separation and the global uniformity of the embedding distributions. Next. And the self-supervised learning is also used in defect detection. It can discover the basic pattern of complex defects and achieves rather satisfactory results, even though the number of the training samples is very small. Next. For the robust manipulation aspect, we consider the situation where the robot has damages. Usually, robots have limited adaptation ability compared to humans and animals in the case of damage. Therefore, we propose the adversarial reinforcement learning framework, which significantly increases the robot's robustness over joint damage cases in manipulation tasks. We validate this algorithm on the three-fingered robot's hand. Okay. The deep reinforcement learning has made a significant progress in robotic manipulation tasks, and it works very well in the ideal disturbance-free environment. However, in the real-world environment, both internal and external disturbance are inevitable. Thus, the performance of the trained policy will dramatically drop. To improve the robustness of this policy, we introduce the adversarial training mechanism to the robotic manipulation tasks, and skill learning algorithm based on software actor critical is proposed for robust manipulation, and extensive experiments are conducted to demonstrate that the learned policy is robust to the disturbance, and it is demonstrated that our demo has higher robustness against the adversary attack than normal SAC policy. Here are some here are some visual demos. Take one aptitude as an example. The video shows that our demo can turn the object while the SAC policy is almost out of function. I'm sorry for the video cannot be shown in this PDF. Okay. The goal of the task transfer in reinforcement learning is mitigating the action policy of agent to the target task from the source task. Given their successes on robotic action planning, current methods mostly rely on two requirements: exactly relevant expert demonstrations or the explicitly coded cost function on target task, both of which, however, are inconvenient to obtain in practice. In this work, we relax these two strong conditions by developing a novel task transfer framework where the expert preference is applied as a guidance. In particular, we alternate the following two steps. First, letting experts apply predefined preference rules to select the related expert demonstrations for the target as a target task. Secondly, based on the selection result, we learn the target cost function and the trajectory distribution simultaneously and generate more trajectories by the learned target distribution for the next preference selection. Okay. Now let's talk about the final lifelong learning for manipulation. The forgetting is of great importance for deep learning and robotics, and recent lifelong learning research has great advances in supervised learning. However, little work focuses on the reinforcement learning. In this work, we focus on evaluating the performances of the state-of-the-art lifelong learning algorithms on robotic reinforcement learning tasks. We mainly focus on the properties of the forgetting for these algorithms and summarize the pros and cons for each category of lifelong learning algorithms when applied in reinforcement learning scenarios. And we propose a framework to modify the supervised lifelong learning algorithms to be compatible with reinforcement learning and develop a lifelong learning manipulation benchmark task set for our evaluations. Okay. Finally, let's come to the summary part of this talk. Okay. Here is a summary of our recent work on dexterous manipulation. We see that the dexterous manipulation is from multimodal perception to lifelong learning. In the multimodal perception aspect, we have investigated the topics of the tactile recognition, soft hand, material recognition for waste recycling, active exploration, cross-modal perception, MQA task, and audio-visual reference expression. In the lifelong learning aspect, we mainly talk about cross-modal material retrieval, self-supervised learning, fault-aware learning, adversarial learning, and a lifelong learning manipulation is also built. Okay. These are some directions of our future work. One is the integration of the environmental perception and the language understanding, such as auditory, visual, tactile fusion, language grounding. The other one is the integration of the multimodal perception and the lifelong learning, which is mainly focused on open environment and the various tasks. Okay. Our work was recently supported by the National Nature Science Fund for key international collaborations, and also PG and Sims also provide strong support for our research on cross-model retrieval and manipulation. We hope to have more collaborations with scholars in this community in the near future. Okay, thank you.